All right, well, here we are at our last part of Lecture 6, and here we're going to look at UV-Vis spectroscopy, so ultraviolet visible spectroscopy, very commonly done with the same machine. We have several at our program, UV-Vis machines, and so they go generally from about 360 nanometers or so, maybe even to 200 nanometers, well into the UV, and they may even go up to like 1,000 or 1,200 or 1,400 nanometers of wavelength into the near IR. So they span quite some distance. They have two separate lamps in order to generate the either the visible light or the ultraviolet light before as it passes through the monochromator going through the sample. But let's look at how we can use UV-Vis machines, UV-Vis spectroscopy, and how it correlates with molecular orbital theory and our character tables. So molecules prefer to have their electrons in their orbitals at the lowest possible energy levels. That's the ground state. We learned about that in our introductory chemistry course. When we shine light onto a molecule, specifically UV light in this case, electrons can absorb the energy of that light. And if the energy of that light is an exact match to the amount of energy needed to get it to that next energy level in your molecular orbital diagram, then that electron can be promoted up to that next energy level. And there has to be space available, so you can't look at orbitals that have two electrons where there's two electrons in the next highest energy level, because even though you may have provided the energy for that electron to jump up, it can't jump up into that next level because there's nowhere for it to go. It's a bit like buying a plane ticket when the plane is full. Great, you have a ticket, you still can't get on. It doesn't matter how much money you put into that ticket, you still can't get on because there's no seat for you. Same idea here. So the orbital cannot be fully occupied. So generally we're dealing with a HOMO-LUMO jump from the highest occupied molecular orbital to your lowest unoccupied molecular orbital. So here we talked about this in the previous lecture without really defining it. So the HOMO, your highest occupied molecular orbital, your LUMO is your lowest unoccupied molecular orbital. And the gap between those two molecular orbitals is generally fairly good sized, but it definitely has lots of things that can influence that energy gap, and it changes what we perceive for that particular compound when it interacts with light. And so the energy gap between the HOMO and the LUMO is usually what determines whether or not something has color that we can perceive. If the gap is sufficiently small and visible light has enough energy to cause a jump of an electron, then we will see the color that remains after the color of the energy needed to make that electron jump is removed from the white light that comes out. And so we see complementary colors. So we see something that may remove red, and if it removes red, we'll see the complementary color of red. If it removes blue, we'll see the complementary color of blue. So if the gap is large enough that UV light is required, then a wavelength of UV light will be removed from what we perceive. But of course, UV light we don't interact with our eyes, and so we won't perceive any color in that compound. And a good example of that is water. The reason water has no color is because the light that takes an electron out of the HOMO of water, puts it into the LUMO of water, is high enough in energy that we can't perceive what's left after that UV light is removed from the UV light that was put into it. Now, both of these last two techniques, photoelectron spectroscopy and UV-Vis, are very similar in the sense that we're hitting a molecule with light, with energy, and we're causing electrons to move from one orbital to another. And they both give us orbital energy information. However, they are very different. A PES is what we can call a cannon. It hits the molecule with so much energy that electrons are completely ejected away from the molecule, and we actually sense those molecules. So we capture those molecules on a sensor so that we know their energy, and from that we can determine what the energy of the orbital where it came from is. So your PES tells us what the energy of orbitals are within the molecule. UV-Vis is a bit more delicate. A good way to look at it is it's the elevator. What you're doing with UV-Vis is taking electrons from one floor and moving it up to the next empty floor. And so when we do that, the information that we get out is the energy difference between orbitals. And so that is also very important when we're looking at molecules, because it does tell us something about how the molecule is constructed and where the energy levels lie. And something when we're looking at UV-Vis spectra and molecules is we want to look at something called the Laporte rule. And that's where we're going to bring in this idea of symmetry in our character tables. So Laporte rule applies to molecules that have an inversion center in their symmetry description, in their operations. So the Laporte rule states that for a molecule to absorb light effectively, the symmetry of the orbital where it started must be different than the orbital where it lands. So if a molecule has no inversion center like water, then the rule does not apply and the electrons can land where they please. However, if a molecule does have an inversion center, something different happens. So you have to remember that molecules with a center of inversion in their symmetry labels will have a G or a U in those labels. Remember, G means gerade and U means ungerade. And so if an electron transition is going from a gerade to an ungerade, or ungerade to gerade, GU or U to G, the absorption of light will be very efficient and you'll get really intense colors. This is really common in dyes. However, if you have an electron transition going from a G to a G or a U to a U, then the absorption is not going to be very efficient. It would be considered to be inefficient. It's not necessarily forbidden because most of these compounds do have a pale color resulting from those electron transitions, but you don't get a lot of electrons transitioning. And as a result, the amount of color that comes out of these compounds is very low. So that finishes out lecture 6. It finishes out our course. I sincerely hope that you found the content and the material interesting, especially in this final week. And as always, if you have any questions on the content, make sure that you contact me.